Okay, so I'm going to start now. Uh, okay, so last week we talked about the first part of we discussed the first part about binary search tree. So we see that basically binary search tree is so in order for a tree to become a binary search to be a binary tree, we require that each node can only have at most 2 children nodes. So this is the binary tree, and also we learned another special type, one special type of the. Let me put it over here. Okay. So we learned a special type of the binary tree named binary tree. So in order for a binary tree to be a binary search tree, it has to satisfy the binary search tree property, which is this. Okay, giving any node inside the tree. So this node should be larger, the value holding this node should be larger than or equal to all the values in the left subtree of this node, whereas it should also be less than or equal to all the values in its right subtree. So if this requirement is satisfied, we call such a binary tree a binary search tree, and so if you remember, we say that the primary reason for us to learn binary search tree is because the current data structures that we have learned basically are array, stack, queue, linked list. So in terms of search, they are just the same, O(n) complexity, because we need to go through every element in this data structure in order to search for an element. Whereas the main objective for us to learn binary search tree is to get a better search complexity or to get more efficient search operations. So so in binary search tree we learned we need to learn 7 functions. So far we just learned 4 of them, which are the traverse function. Traverse meaning we want to go through all the values and go through all the nodes and print all the values in the tree. So there are 3 different orders for us to do the traverse. So we say they're in order, pre-order, and post-order. So this is the explanation of these 3 different orders. So in which order are we going to print all the values from the smallest to the largest?
In order?
Yes, that's in order. And so the explanation is here, okay? Because in order, we're going to visit for any node x, we're going to visit its left child first, then x, then its right child. So they satisfy this relationship. So that's why we can print out values from the smallest to the largest. And then then we learned another function named search. So search is to search for a certain value inside the tree. So here we got an example. Suppose this is the tree that we're giving. Suppose here we want to search for the value. Let's say, for example, 17. From the root node, are we going to go to check its left subtree?
No.
No, because 17 is larger than 15. So all the nodes in the left subtree of the root node are going to be smaller than 17. Okay, so which is definitely not out of our interest. So then we're going to go right, and then we go another left. So basically, with the organization with the binary search tree property on each level of the binary search tree, we only need to visit at most 1 node in order to search for a certain value. So
Hey, Professor, I don't think any of us can hear you.
Yeah.
I thought it was just my computer. I was going through my settings.
Yo, is he talking or no? I can't hear him.
He's trying to fix it.
Okay.
Can you hear me?
Yeah, not,
Yeah, I can
not
hear you.
clear.
Okay.
Yeah, now okay. Yeah.
Okay, but it seems that my screen got stuck, right? So can you see my writing? I just read some random thing. Okay, I think finally, yes, it shows. Great. Okay, cool. So okay, so before that, I was asking, okay, what is the okay, let me repeat that. Because with the binary search tree property, so it guarantees that when we want to search for value inside in a binary search tree, on each level of the tree, we only need to visit at most one node. So what is the search complexity? Can you hear me?
Yeah.
Oh,
Okay.
then
Is it
No, it's not ON.
OH?
Yes, so I wrote it over here. OH.
It's for
H
height,
is
right? Yeah.
Yes. Yes, H is the level of the number of levels in the tree. So because on each level we are going to visit at most one node. So in total we are going to visit at most H nodes. So that's how we got the H complexity, OH complexity. And so how do we find the minimum and maximum value inside a binary search tree?
We just, I'm guessing, first check if it's empty. If not, we'll just see based on the rule value if the number is smaller or greater. If it's greater, we look to the right. If it's smaller, we look to the left or recursively.
Oh no, that's the search. What we are talking about is search. But here what I'm asking is how do we search for this? How do we find the smallest and the largest value inside a binary search tree?
Isn't the smallest value all the way to the left and the
Yes.
biggest is right, all the way to the right?
Yes. So we just so to find the smallest value from the root, we just go directly to the leftmost place. And then to find the maximum value, we just keep going, keep turning right until there is no more right. So so this is how do we find the minimum and the maximum value inside the binary search tree. And here is another example. So we wrote it over here, right? So here to find the minimum value, we just need to start from the root, keep going left. To find the maximum value, keep going right. So the complexity for us to find the minimum and the maximum value inside a binary search tree is also OH, where H is the height of the tree. And also last week, we spent a long time explaining what is the relationship between H and N. So what is the relationship between H and N?
H is the height of the tree, and then N is the number of nodes, I think.
Yes.
Okay.
Is there a relationship between these two values? So last week we spent a long time discussing it over here, right? So we explained that the conclusion is that h is less than or equal to n, but larger than or equal to log n, right? And in most cases, we say that in most cases, we can get close to log n height. Okay, in most cases, we got this. So then, which means that in most cases, we got log n search complexity. But in the worst case, still we can get O(n) search complexity, because if h equals to n, still we need to go through n nodes inside the tree in order to find the value. So, make sense?
Yeah, that makes sense.
Okay, and in practice, we want h to be as small as possible. So we want it to be as close to log n as possible. Okay, so but that's hard to control. And today we're going to learn another tree that is more advanced, which can make sure that h is log n. So, okay, but we will learn it later today. So okay, so so here next today our main task is to learn the other three functions of binary search tree, which includes successor, insertion, and deletion. So among these three, we're going to pay more attention to the successor and insertion. Whereas for delete, we're going to briefly discuss it, and because it's too difficult. And then after that, we will learn two new data structures. The first one is called arbitrary. Arbitrary is the one which guarantees that h equal to log n. Okay, and then we will learn another data structure called hash table. Some of you may have already heard about it, but still we are going to discuss it in our class. So okay, and then let's look at the successor function. Okay, so I'm going to use it as an example. What is the successor? Okay, so I'm going to give you this. So if we are talking about the successor of a certain node, if x is a node, okay, so then we say y is x the successor of x if y holds the smallest value. Larger than x. Okay, so basically we want to so if we want to find given x, if we want to search for its successor, basically we're going to search for another node which holds the smallest value than x in the binary search tree. Okay, so here let me give you one example. So suppose here we want to search for the successor of, let's say we want to search for the successor of this node. This is x. Where is its successor?
9.
Yes, the node that holds the value 9, because 9 in this binary search tree, 9 is the smallest value that is larger than 7. So great. So this is the successor of this node. Okay, we say this is I'm using this line to denote. Okay, so y is the successor of x. Okay, cool. And then let me give you another example. Okay, suppose here we want to look for the successor of the node 13. Where is its successor?
It's the original node 15.
Yes, this is the root node.
The
The root node is the successor of the node that holds the value 13. So because in this binary search tree, 15 is the smallest value that is larger than 13. Okay, so any question with regard to the definition of successor? No? Okay. So if you want to look at the formal definition of successor, it is on this page. Okay, a tree node that contains the smallest value greater than x. Okay, so and let's say how to search for that. Again, we will come back to this example. Okay, here let's look at the first case where we have x here, and so here let's say, does x have a right child?
Does X have a what?
A right child?
Yeah.
Yes, this node has a right child. Okay, so if this node has a right child, basically it's going to have a right subtree, right? Or we say the subset of the tree that goes to the right of this node x. We call this the right subtree of x. So are all of these values larger than or equal to x?
Yes.
Okay, so in order to find the successor of x, basically we are going to search for the smallest value in this area. Correct?
I have a question. Can 13 have a child on the left subtree smaller than 7? Like another 6, for example?
Can 13, so okay, his question is this. Okay, can 13 have a left, let's say, descendant that is larger than 7? Something
No,
like this.
No, can
Right.
13 have like 6, for example, on the left subtree?
No, you can't.
Yeah.
Can 13 have 6?
Yeah.
No. The thing is that all the values, if you look at the definition of the binary search tree property, so all the values in its right subtree are going to be larger than it, and then all the values to its in its left subtree are going to be smaller than it. Okay, if we come back here, if you have 6 over here, then this part is the right subtree of the node x. So all of these values should be larger than or equal to 7, but it violates the requirement. So this is not a binary search tree. So the answer is no, we can't.
I see. Okay. Thank you.
No problem. Okay, let's come back to it here. So we say that this is the right subtree of the node x, and we said and so because of the binary search tree property, we know that we're sure that all of these values are going to be larger than or equal to x, right?
Yes.
So
Right.
yes, so in order to find the successor of x, we basically only need to find the smallest value over here. Correct?
So it's just the leftmost node.
Yes. So basically, we only need to call the minimum function over its right child. So if you look at the definition of the minimum function, it's over here. Given a node x, we keep going left at the starting from the node x. We keep going left. Okay. So here we just need to call the minimum function over its right child, over the right child of x. And then we will be able to find the smallest value in its right subtree, right?
Yeah.
Okay. So then this logic is pretty simple. So if x has a right child, so we have y which is the parent, which is the successor. Let's do not use y. Let's use z. Sorry, let me use z rather than y to avoid the confusion. Okay, then z, we have z as the, we just call the minimum function over the right child of x, and then z should be the successor of x. Make sense?
Yeah, that makes sense.
Okay, so okay, so then let's look at another case, another case that we just discussed. So which is over here. If this is x, does this node x have a right child?
No.
No.
No, so we cannot apply this rule. We cannot call the minimum function at its right child. So okay, so since it does not have a right child, and so there are only two ways, there are only two directions for us to go to find its successor. The first direction is to go left because it has a left child. Can we go to its left child to find the successor?
No, there's no successor has to be greater.
Yes, the successor has to be greater. So it does not have a right child, but it has some left part. Okay, so this means that we cannot go to its left child. There's no chance. We shouldn't even look at it because so this part.
Did he go mute for you guys?
Yeah.
Yep.
Yeah.
Yeah.
Okay, while he's mute, I have a question. So if 9 can have like a 7 as a left child, could it?
No, yeah, I can. Because
Okay.
it's less than
Yes.
9 and 13.
Like the right subtree of 7, it just has to be equal to or greater than, right?
Yeah, it has to be less than or equal to.
No, the right subtree.
All right, yeah. Yeah, greater than or equal to.
Okay, perfect. I've actually had this happen on Zoom quite a few times, and just leaving and coming back actually like works for me.
Zoom.
Yeah.
Yeah. Mm-hmm.
Are you guys keeping up with all this?
Like, do I understand?
Yeah, no, like all this information. I mean, like,
Yeah, that makes sense.
It
But,
does
like,
make
if-
sense. Sorry.
No, my bad. But like I have like I have a general concept, but like I can't go into it like specifically, I guess.
Quickly getting up. I'm putting my thing in my class, bro. Don't make me beat you up in out here, bro. There's no cops here, bro. No cops.
yeah.
Okay. Can you hear me now?
Yes.
Yeah.
Yes.
Okay, cool. So so previously we said that okay, starting from the node x, we cannot go right because it does not have a right child. We cannot not go left either because if we go left, we will only be able to find values that are less than or equal to x. So it cannot be the successor. So then the only route that we can go is to go up, right?
Mm-hmm.
Okay, so here let's go up by one step. Okay, let's go up by one step. So here we are making a left up, correct?
Yes.
Yeah.
Okay, if we go up and left, what does that mean?
We have to continue.
Yes, it means that the value that we observe is less than or equal to x, the value at x, right? Because of this relationship. If x is the right child of its parent node, this node, then we know that x is going to be larger than its parent. So which means that so when we go up, we just observe a value that is smaller than the value at x. Correct?
Yeah. That makes
So then we say, okay, we cannot stop. Let's go another up. But here we are still going up left. Okay, so it means that we see even a even smaller value. So then we should go another up. Okay, this time we go up and right. Correct?
Mm-hmm.
So this means that this value is going to be larger than or equal to all the values over this area, and including x, correct?
Yeah.
Okay, so this is the first value that we observe that is larger than or equal to x, and this is the successor of x. We stop. Make
Is
sense?
it possible? Is it possible for a node to have two successors?
No, just one. Just one successor. If there is a dual, we just pick either one of them.
It doesn't matter what you pick.
No.
Okay.
Okay. So then the else is pretty simple. So if x does not have a right child, we will do this. Okay, we are going to keep going up until we make the first right upturn. This is what we did over here, right?
Yes.
Okay, so this is the logic for us to find the successor of a node x. Any question?
Why do we need to find the successor?
Okay, so that's a very good question, and let me say, we will. So this function, the successor function, is used in the deletion function. It's called by the deletion function.
So we're just leading up to the deletion function, essentially.
Yes, yes. But for deletion function, we're only going to have a very lightweight touch of it, because it's too complicated.
So I'm assuming it's extra credit.
No, I don't think I even included it in the extra credit. It's not worth it. If you go to a job interview, no one is going to ask you to implement the deletion function. You cannot even memorize the pseudocode in your mind when you go to a job interview. You've got too many things to remember.
This is a very practical class. Like I feel like your goal is to just prepare us for a job interview, like to get a job.
Yes, that's what I want to do. And I don't want you to get embarrassed or say lose your confidence from your job interviews. Okay. So here, and so this is what we so this is the logic of the successor function, and here I just write it down in the slides. It's over here. The key idea is that if x has a right subtree, we just call the minimum function at its right subtree. Otherwise, we will find the first ancestor of x that is on its right side. So that's the same as what I said before. Keep going up until we make the first right turn. Okay, so this is the pseudocode. If x is not nil, if x dot right is not nil, meaning that x has a right child, we just call the minimum function. Minimum function at x dot right. So I think this is exactly the same as what we lay out over here, right? Correct?
Yes.
Okay, so then I'm going to skip that part. I'm going to skip this part. Instead, I'm going to focus more on the else part. So if x dot right is nil, so remember, if x dot right is nil, what we do is that we just need to keep going up. We just need to keep going up. So let me put it over here. Keep going up until we make the first right turn. Okay. So okay, let me make x over here. Let's see what do we do with this code. So here, this is our start. We have x here, and let's check. Okay, x dot right is nil, so this condition fails. So we go to line 3. We are going to go to line 3. We have x equal to y equal to x dot p. What does p stand for?
The parent.
Previous?
Yes, the parent. No, the parent.
Oh, parent.
So if you remember, in the last lecture, we said this, we introduced this. Each tree node consists of 4 pieces of information. The key, P is the tree node, the parent node, and then left and right child, okay? So here, x dot P means
Professor,
say it.
by parent node, you refer to the root, right?
No.
Here, over here, I wrote the root because I was taking the node 5 as an example. So if we take this node 5 as an example, then its key is 5.
Okay.
Its parent node is just the root. Okay, so here, so say the parent of x is basically the node over here, right? The node that stores the value 7. Okay, so we have y as here, and okay, so let's say while x is not nil, so obviously this is true. So y is not nil, and x equal to y dot right. So is this true or false? Is x the right child of y?
Yes, it is.
Yes, this is true again. So this basically, if this is true, it means that we are going up left. Okay, so if x is the right child of y, when we go up, it's like we are going to go up left. Correct?
Yeah.
Okay, so while we are going up, while we are going in the up left direction, what we do is this. Next, we will have x equal y. So we will assign y to x. So the new x will be here. Okay, and then the new y will be the current parent of y. So which is the node that holds the value 6. So the new y is going to be here. So basically with these 2 lines, what we do is that we move both x and y one level up. We move x 1 level up, and we move y 1 level up. Correct?
Yes.
Yeah.
Okay, so this is like move up by 1 level. Okay, while we are going, so if we translate this while loop into a human language, it will be while we are going up left, we just go up. So okay, so then let's say next after this we have y here and x over here. This is x and this is y. So let's check if these conditions are true or not. So so here this is true, right? Because y is not nil, obviously. And is x the right child of y? Is this true
Yes.
or false?
That's true.
Yes.
Yes.
Yes, this is true. X is the right child of Y. So this is also true, meaning that we are going, if we go up, we will go up in the left direction. Okay, so then we just go up, we just move up. So then when we execute the next two lines, we will have X equal to Y. So we move X over here, and then we are going to move Y to the parent of Y. So the parent of Y is basically the root node. Okay, so so then here you can see that we are moving X one level up and Y one level up. So so this is what we do, and then let's remove the old values and have the new values over here. So okay, let's come back to the while loop. While Y is true, Y is not nil. So this is true. Y is the root node. It's not nil, and X equal to Y dot right. So is this true or false?
It's false. So you just
False.
return Y.
This is false because this node, so X is the left child of Y. So this is going to be false. So we just terminate the while loop and then return Y. And so this is the successor of the node that holds the value 13. Okay. So basically, this is like while we're going up, what we do over here is that while we're going up left, we go one level up until we make the first right turn. We will only stop until we make the first right turn. Exactly the same as what we said over here. Keep going up until the first right up. Right?
And this is why you said that it doesn't matter if it has two successors. You just pick either one, because if 17 had a left child of 15, it would still just pick the root node.
Yes.
Yeah. Okay, that makes sense.
Okay. Cool. So cool. So then any question with regard to the successor function? Okay, so then here, let me ask you one question. Guess what is the complexity of this function?
Let's see.
So it's either OH or log N.
It's OH. The reason is that if this is the node that we want, if this is the node X and we want to look for its successor, either we go down by at most H levels, or we go up at most by H levels. So that's why we got the OH complexity. Make sense?
Mm-hmm.
Okay.
Yes.
Sure. So then this is the successor function. Okay. And next, let's look at the insertion function. Actually, the insertion function this is the pseudocode of the insertion function, but indeed it's very similar. The insertion process is very similar to the search. So let's look over here. Okay. Suppose I'm going to draw an example over here. Okay, so suppose that we have a binary search tree as this, and then we got a new node Z to insert, which holds the value 13. So let's say where should we insert it? Okay, so again, we start from the root. We always start from the root. From the root, where should we go?
the right.
Yes, we can only go right because 13 is larger than 12, so it can only go to the right subtree of the root node. Okay, so after we make a right turn, and then here we know that we should make a left turn because it is less than 18, so it can only reset in the left subtree of 18. And then we reach the node 15. Okay, so since 13 is less than 15, it should also reset in the left subtree of 15, correct?
Yes.
Okay, so then we should also make a left turn. Okay, but here after we make a left turn, we are reaching a new node. So we call this node X. Okay, we call this node X. We reach a new node. A new node means this. Okay, this is an empty space. This space is available. It has not been claimed by any other node. So this place is free. So that is the place for us to insert the new node Z. So this will be the, so we are going to put the new node Z over here. So is it pretty much like the search?
Yeah.
Yeah.
It's going through one node each time.
Yes, we just by using the value comparison, we are directed to the position where we should insert insert the new node. Okay, so then but here if you look at the pseudocode of the insertion function, it's really complicated. Here I'm going to explain to you why it looks much more complicated than search. Okay, I'm going to draw the example right over here so that it's easier for you. Okay, this is the new node Z. The new node Z that we want to insert. Choose the value 13. Okay, so this is the new node Z, and so let's start. So here we got T. So it takes two input parameters, T and Z. T is the tree, and Z is the new node to be inserted. So here first we have Y equal to new and X equal to T dot root. So we're going to put X over here because X is the root of the tree. So if X is the root, no, shouldn't do that. Shouldn't do that. So if X is the root of the tree and Y is new. So if I tell you that there is a relationship between X and Y, and what kind of relationship could that be? Again, if X is the root of the node and a root of the tree, and Y is new, what kind of relationship can exist between X and Y? Think about it. Any idea? Y is
If
a
Y
child
is
of the root? No, Y is not the child of the root.
if Y is null, then is it the function that you're trying to insert?
No,
Is it the node? No. Okay.
no. So let me ask you one question, okay? Let's come back to the other slides. So, over here. So instead of tree, which node? So how many nodes have a new parent?
Just one, the root.
Yes. Okay. So come over here. Okay, if X is the root node and Y is new, what kind of relationship can exist between x and y?
I mean, then it would be like if a parent did exist of the root node, then it would be that. But like I don't know actually.
Y is the parent of x, which is new. Okay, so y is always the parent of x. We always keep this relationship when we're going through the code.
In every binary search tree, y is always the parent of x.
No, here we're just
Yeah.
creating these variables in this way. So because when we're doing the insertion, we need to create these two variables, and we keep the ratio, the parent and child relationship between x and y.
I see.
Okay, so y is the parent of x, and we're going to maintain that relationship. Okay, so while x is not new, as I've said previously, we're going to keep so going down till we find a new node. Okay, so and then that is the place where we should insert the new node z. Okay, so let's say while x is not new, while x is not new, so here we got this as true. We have y equal to x. We are basically going to move y and x one level down. So we have y over here, and if z dot key is less than x dot key, so we have z dot key as 13. Over here is 13. What is x dot key?
12.
12. So this is false. And then we should go to execute the else. We have x equal to x dot right. So we move x to its right child. So we got x over here, and you can see that here. We move both x and y down by one level, and still y is the parent of x. Okay, so this is the first step and the first iteration, and then so let's come back here. Okay, so so then we go back to the while loop again. If check if while x is new or not. So obviously x is not new, and then we have y equal to x. So we are going to execute y equal to the line 4 with y equal to x. So we're going to move y over here, and then we're going to have the value comparison. Z dot key remains unchanged, it's 13, but now x dot key is 18. Okay, so this is true, and then we will be able to execute line 6. We have x equal to x dot left. So we're going to move x to its left child. So we move x here, and we move y here. Again, we are moving x and y one level down in the binary search tree. Oh, sorry, this is y, this is y, okay? Okay, so y is still the parent of x. And next, we go back to the while loop, and then we compare x with new. Obviously, this is true. So then we can execute line 4 with y equal to x. So we're going to move y one level down over here, and then we're going to have we're going to compare x the key between z and x. Z dot key is still 13, but x dot key here we have x dot key as 15. So this is again true. So we're going to have x equal to x dot left. So we're moving x to its left child over here, which is a new node. Okay, so it's a new node, and then okay, so I'm going to write y over here, and then we're going back to the while loop. So here we can say that this condition now fails because x is a new node. So this condition just fails, and then we terminate this while loop. So as what we said previously, okay, here we just find, okay, we should put z, we should insert z to the place of x, and so then finish the insertion, correct?
Yes.
Okay, so next we have z dot p as equal to y. So basically we're assigning y as the parent of z. So this is equivalent this is like doing this. We're saying the new node Z, the parent of Z is Y. Okay, we're saying that the parent of Z is Y. But what we are not clear is that if we should put Z as the left child of Y or the right child of Y. Okay, so next we have this. If so, we're going to figure it out with the last 6 lines. If Y is new, so what does that mean if Y is new?
I mean, it's not null, but
Yes, over here is not new. But what if Y is new, what does that mean? Remember, this is the starting point, right? Initially we have Y as new, correct? And then we're going to move both X and Y down. If Y is new, it means that we never execute this part. So it means this, the root node of the tree is new, correct?
Yes.
Yeah.
Okay, so if this is true, it means this, the tree, basically the tree T is empty, because even its root node is new. Okay, it does not even have a root. It's like we got a family with nobody. And then so if we're inserting a new node into a empty tree, so the new node will be the root of the tree, correct?
Yes.
Yes. Okay, so this is what we do over here. If the tree is empty, then we're going to take the new node Z as the root of the tree. So otherwise, which is our case, otherwise, if Z dot key is less than Y dot key, we're basically comparing the relationship between Z and Y in order to know if we should put Z as the left child or right child of Y. So in our case, we have Z dot key as 13 and Y dot key as 15. So this is true. So we're going to execute line 12 and assign Z as the left child of Y. So with this line, it's like we are officially putting the new node Z over here as the left child of Y, and then we finish the insertion process. Okay, make sense?
Yeah, that makes sense. For a line 9, does that mean, or line 9 to 10, does that mean there's only one element then? Because it's only one node.
You mean line 9?
Yeah, there's because like you said it becomes the
It
parent.
means that we got a tree with an empty root node. So basically, the tree does not exist. It's totally empty. It does not even, the tree does not even have a single node. So it's like we are inserting a new node Z into an empty tree, and then this will be the new node Z will become the
parent.
root node of the tree.
Yeah, so it's only Z. The
Yes.
only element is Z.
Yes. Yes.
Okay.
After the insertion, only Z exists in the tree.
so you're creating a new tree essentially, and then
Yes. Yes, you can take it in that way. First, if it's in Java, first we are going to create an empty tree and then insert a new node into it. That's how we finish creating a tree with at least one node. Make sense?
Yes, makes
So-
sense.
But any question? Okay, so and let me say over here, okay, guess what is the complexity of search?
Is it O of N?
No,
It's
we
still
need to
OH,
visit
right?
all the nodes. So here you can see we ignore this node and also this node. So what could the complexity be?
Then it's still OH.
OH, yes, it's still OH because you can interpret it or understand it in this way. The first way is that the insertion is pretty much like search. And so because search has a OH complexity, then insertion also has a OH complexity. And to understand it more concretely, so initially we have X over here, and then we in each while iteration, the iteration of the while loop, we move X one level down. So in total, we can move it H levels down. So that's how we got the OH complexity. Okay. So any question for the insertion function? No? Okay, so then let's look at the last function. It's called delete. So so the idea of delete is this. Okay, suppose okay, so this is we got a big tree. So X got its parent. X has their X got its parent. So the parent of X can either be at this side or this side. So to make it general, I'm just going to say this, okay? Z is a node of the tree, and here Z got its parent. So no matter on its left side or right side, okay? So and then so we basically want to delete this node Z from the binary search tree. Okay, and let's discuss this deletion process. I'm only going to talk about it in a very simple manner. So the easiest case comes from this. Okay, comes from this. Okay, we are deleting a node Z that does not have any node. Does not have any child node. Okay, so that is going to be really simple. We're only going to go to its parent. We're going to go to the parent of Z. Said, okay, so let its parent break the relationship. Say that this child is no longer mine. We're just going to break this relationship. Okay, make sense?
Yeah, that makes sense.
Okay, so and then this is the simplest case. Z has no child. Okay, and then a relatively easy case is that if Z just have one child. So here, let's say here we can say that Z only has one child, only has one right child. So we're going to, if we want to remove Z, we're going to let its child, the only child of it, replace its position. We're going to move its child to the position of Z. Okay, you can interpret it in this way. Okay, let's say around 30 or 40 years ago, in my home country, they got this rule. Okay, so if your father retires, and say your father can appoint one of his children to inherit his position. Okay, so my uncle replaced my grandfather's position. So yes, it's pretty much like that. So if Z retires and if Z only has one child, it's pretty simple. We just let that child inherit its position, no matter if it only has a left child or a right child. Okay, again, simple, right? Okay, yes. And then a more complicated case come from here. Okay, so this is the real trouble. Okay, so here if Z has 2 children nodes, if the node Z has 2 children nodes, and so if Z has 2 children nodes, we need to look at this case. We just look at its right child. If its right child does not have a left child, if its right child does not have a left child, we just let its right child replace the position of Z. We just move it up. Okay? And the most complicated case comes from here. If Z has both left and right child, but its right child also has some left child. Okay, so what we do is that we're going to find the successor of Z and let its successor, which is basically the smallest value in its right subtree, the smallest value over here. And then let the node Y replace the position of Z. Okay, so this is what we do. And this is the complete code. So I'm not going to ask you to implement that because this is really difficult. So even though you will need to implement a similar function in your job, you will be giving the pseudocode. So you'll be given sufficient time. You can easily trigger some bugs over here, and it's hard for you to debug it. Okay, so then this is the deletion function of binary search tree. And again, its complexity is OH. Okay, so here I just want to briefly summarize the 7 operations that we have learned in binary search tree. So in binary search tree, we learned traverse function, search, minimum, successor, maximum, and successor, insertion and deletion. We can see that among these 7 functions, except for traverse, all the other functions have OH complexity. All of these 6 functions have OH complexity, which means that the performance of the binary search tree heavily depends on the height of the tree. So remember that we say that H can be as small as log n, but can be as large as n. So we generally want H to be as small as possible. So the search, if we want to search for a value in the binary search tree, we can get a very high efficiency. The search process can be very efficient. Similarly, the deletion and insertion can also be very efficient. So what we do is that we want H to be as close to log n as possible. Okay, do you know what I mean? Do you know why we want it to be as close to log n as possible?
To minimize the runtime?
Yes, to reduce the execution time, to improve the performance of a binary search tree. Okay, so this is what we want to do. But with binary search tree, so it's possible that we still get this, a tree with only one, with only right child or with only left child. In that case, it's pretty much like a linked list. And then in this case, we have H equal to n, because on each level of the tree, we only have one node. So if we are very unlucky and we hit this corner case, and then the performance of binary search tree is going to be really bad. So we want to avoid this case, okay? And we want H to be as small as possible, as close to log n as possible. And to do that, okay? People just design that structure named the red-black tree. Okay, so the red-black tree is really the design of it is really complicated. So the reason why we call it a red-black tree is because we are going to assign each node in the tree a color. So each node can either be red or black. So this is the requirement. So a red-black tree is basically a binary tree that satisfies the following 4 properties. First, the following 5 properties. First, every node can be either black or white, and the root node has to be black, and every leaf node is black. And if a node is black, then both of its children have to be, if a node is white, then both of its children have to be black. For each node, all the paths from the node to its descendant leaves contain the same number of black nodes. Okay, so this is an example of a red-black tree, and the whole point for us to design such a complicated tree is because it guarantees that the height of the tree is this. Okay, so which means that if the search or the insertion or whatever operation on the tree is guaranteed that you will get O log n complexity. Make sense?
Mm-hmm.
So basically, from here you can say that red-black tree is basically a more complicated version of binary search tree, but it gives us one advantage, that is it's going to be really fast. It's guaranteed to be fast. Okay, so this is pretty much like this. Okay, so if you want to, so binary search tree. And red-black tree. Okay, so you can take binary search tree as a, for example, as a say Toyota. Okay, and then the red-black tree you can take it as a Porsche. Hope that I hope that I write Porsche correctly. So so red-black tree is relatively simple. The organization of the tree is relatively simple. It's easy for us to maintain it. But so it's simple but slow. Okay, and Porsche is complicated but fast. Okay, so these are just 2 different versions of that structures. And in practice, even though RB tree guarantees more efficient operations, most people choose to use binary search tree because it's simple for us to implement. Same as the real world, right? We see way more Toyotas than Porsche. So yes, and that is what we have. Also, what we have in real life. Okay, so I just want to have this brief introduction of the red-black tree tool. This is basically what all you need to know about it. You are not going to implement it in your life, even though you are a software engineer. So based on red-black tree, people design a more advanced version of it. It's called a B tree, and this tree is more widely used. So you can take a B tree as a Ferrari or something, or Lamborghini. So this one is faster, and but contrary to Porsche, B tree.
Did he cut out for you guys?
Yeah, you did.
Yeah,
What was a leaf node again? What was a leaf?
those are just child,
Those are just childs?
or like the isn't it the last like nodes?
I just Googled it. I don't know why I didn't before.
A leaf
It doesn't have a
a node
child.
with no child.
Yeah. You Googled it too? Yeah, I was looking it up. Thanks, man. I appreciate it.
I got curious. Yeah, for sure.
Yeah, it's basically
Did
the
it-
last node.
I can see his face trying to work on it, but but I can't hear him.
Okay, how about now?
Yeah, we can hear you.
Yeah, we
Okay,
can hear.
sorry
Yeah, we can
about
hear.
that.
Mhm.
I'm not sure what's happening, but it seems that my home internet is really bad today. So okay, so over here, okay. Where did I stop?
Ferrari, the
B3.
B3 is
Ferrari,
Ferrari
Ferrari.
okay.
B3.
So B3 is the basically the Ferrari in terms of the execution speed and complexity. It's really complicated. It's, but we still use it a lot in practice because if we build a database, we need to do a lot of searches. For example, if we build a database for the students in Montclair, a lot of people are going to search for students, let's say with a balance, with a high balance in their account, search for students who are going to graduate next semester, or search for students with a relatively high GPA to give them some scholarship. So for those cases, because in database, we're going to perform a lot of searches. So it's going to be very worthwhile to design such a data structure like B-tree, which guarantees a very fast search. Okay, so that's why we have this B-tree. Basically, every database is implemented in a B-tree. So that we can get a very high search efficiency. This is pretty much like if you are if you are going to go to the Formula One, even though a Ferrari costs you, let's say, $30 million, you have to pay it because that's your job. You're going to race every day. Make sense?
Yeah, makes
Yes.
sense.
Okay. So, but we're not going to learn B-tree, and you are only going to learn this data structure if you pursue a master. That's too difficult. So, and also previously I heard one question before I was interrupted. I heard one question that is what is a leaf node? A leaf node is a node that does not have any child. Okay.
Yeah, we were talking about it. We looked it up while you were
Okay.
having issues.
Okay, sure. So okay, so then we just finished the red black tree. So I think I have time for you to ask me 2 questions today, like what we did the last time.
Do you recommend, is a PhD worth it if you want to go in the industry, or is a master's like sufficient enough to command the highest salary?
I mean, this is a very good question. If you are determined to go to industry, don't go for a PhD. It's going to take too long. And if you just want to be a software engineer, a master degree is good enough.
Would you still command the same salary that your 2 friends at Facebook did?
I mean, you mean their salary? So
Yeah.
no,
like
so if you don't have a PhD, you will not be able to get that crazy amount of starting salary, 300K. So that's not going to be possible. So I have a friend. So I previously I had a lab mate who quitted his PhD and only got a master degree and joined Google. So I think his starting salary is like 130K. Okay. So, but the thing is that you save 3 years. You save 3 years. Okay. So because if you just want to go for a master degree, it usually take you 2 years. And if you want to go for a PhD, you need to pay 5 years. Okay. So you see that PhD is basically a master plus 3 years, 3 more years. And if you work very hard, if you got a master degree and work very hard, and in 3 years, you will be able to make your salary go from 170 to 300 in 3 years. So, yes.
I see. Also, you said that your friend had like a 400 starting salary with the sign-on bonus and the stock, but I know the
Yes.
sign-on bonus and the stock is like a one-time thing. So after like the first year, the salary is significantly lower than the 400K.
No, they're going to refresh your stock. Give you
They
more
give you more
stocks.
stock every year?
Yes.
Okay.
I have a
What should
question.
they typically give in stocks?
What? Say it again. I didn't hear you clearly.
How much do they typically give in stocks?
It depends, really. It depends. If you only have a bachelor degree, your stock is minimum. But if you have, let's say if you have a PhD degree, so this is also depends on your skills. So for example, I'm not exactly sure, but I think for Google, they have different levels of jobs. So level 3, starting from level 3 to level 4, level 5, level 6. So if you get a undergraduate degree, so your starting level is going to be L3, and at the time when you join, so the stock that you can get is at most 20K, at most, max. So if you got your master, you start as L4, and then your stock. So they were going to give you some stocks in, let's say, around 100K in the first 3 years. So each year you are going to get a portion of the stock. And so if you got a PhD, so you're going to be either L5 or L6. So that's why you got a much higher salary, a starting salary plus more stocks. So this is, if you got, I'm not sure about L6, but I know something like L5. For L5, your stock is around 160 for 3 or 4 years. And after that 3 or 4 years, if you stick to that company, they are going to refresh your stocks.
Professor, I have a question.
Say it.
I've been noticing one thing is that till now, we've just learned only about sorting algorithms. We haven't learned like any other type of algorithm, like some
Search.
solving algorithm.
You also learn search, right?
Yeah, but we learned how to sort, but like, let's say not some like machine learning algorithm or some like chess algorithm.
Okay, you are talking about machine learning. So how is your linear algebra?
I mean, it's like high school level, I'd say.
Okay, so if you want to learn machine learning, basically you need to understand some papers like this level. Let me show it to you. No, these are too simple. Okay, this paper is too simple. Maybe I can show you something else. Reinforcement learning. So here, this is the reinforced learning algorithm. I'm going to show you the one that say OpenAI use it to train a bot that beats the best player in the world on Dota 2. So let me find that paper. Exploration, no, not a rainbow, reinforcement learning, RMax, PPO, policy transfer, maybe input testing. Okay, yes, this is the one. This is the PPO algorithm that OpenAI designed a couple of years ago. So do you think that you can understand all of this math?
I mean, not right now, but
yes.
Like,
so I mean,
maybe the concept.
Yes. So
if like in Word, I can maybe understand the concept, but not the math right now.
Yes. So the thing is that machine learning is basically an extension of math to computer programs. So or basically we're going to use computing programs to solve some very complicated mathematical equations. So in order for you to learn machine learning, you need to understand this. So with that being said, if you want to learn some machine learning algorithms, you should definitely go to a graduate school. First, in your graduate school, first brush up your math so that you can understand this, and then learn machine learning and also learn coding for that. It's not the time. I mean, if I'm definitely willing to talk about machine learning algorithms, but I think I probably will lose 90% of you. Yeah,
I have even more questions. So I have an associate's degree in IT with a track under cybersecurity, and I was just wondering if I complete my degree here, what do you recommend for something like that.
So if you complete your bachelor degree in cybersecurity at Montclair,
Well, I don't know if it's under cybersecurity. It's under information technology, but
Okay.
at County College, I took the track of cybersecurity, and that's what I graduated with over there.
okay. So I mean, I'm not sure because everyone has a different situation, like finance situation, or say a different career objective.
Mhm.
So in terms of, let me say, so if you just want to make money, let's just be frank, okay? If you want to be rich, and so in the CS world, in the computer science world, if you want to be rich, go for either one of the following three directions. The first one is machine learning.
Mhm.
So the second one is cybersecurity.
Okay.
And then the third one is, software engineering.
What
Okay,
about
just these
big
three.
data?
Big data is a part of machine learning. So,
Oh, okay.
okay, so just go for these three areas. And so like, it depends on your interest. So choose one of them. And so
Okay.
if you want to go for these two, you have to be a math guy.
Okay.
But say if you don't like math, so software engineering is the only way. But say if you work in this area, if you want to have a career as a software engineer and be rich, you have to work long hours.
Okay.
Like be prepared for 60 hours a week.
Okay. Thank you.
Wait, so when you said they refresh his stock, that means they give him more every year, more stocks?
Yes. Like a very close friend at Snapchat. So he joined Snap like in 2016. So if you look at the stock performance of Snap, it's like so it first increases a little bit and then it keeps dropping, and now it goes up a little bit. So what he told me is that when the stock price dropped, even though he hasn't collected all the stocks that the company gave him at the time of employment. So because the stock price drops, the company is afraid that they may lose some of their employees. So they keep giving them more. So it's like the more it drops, the price drops, the more new stocks you get. So, but after that, recently the Snap stock just increases a little bit. So that guy showed me his stock portfolio. I think now he's worth, after like he joined that company in 2016 or 17. I don't remember exactly. But now his stock what he showed me is that he has around 3 million in his stock.
In stock alone?
Yes. He just bought
Okay.
a house like $2.3 million in Manhattan Beach, Los Angeles.
Oh, so he works in Silicon Valley?
Sorry?
Does he work in Silicon Valley, like in California?
He works in Los Angeles. His office is based in LA.
I always assume when people get paid that much that they're in Silicon, they're in like the Bay.
Right, they pay higher than the East Coast. At East Coast, it's the max you can expect is $300 a year, including everything. The max.
I mean, yeah, I guess that makes sense because you gotta consider cost of living and all that.
Who wants to go to California? I don't. So
People are leaving
Nobody.
California.
Nobody.
yeah, I like to visit a couple of cities in California, like San Diego, but not San Francisco, not LA at all. So
Santa Monica's also best.
yeah, Santa Monica is fine, but it's also super expensive over there. If you want to buy a small apartment, like 2-bedroom apartment, it's going to cost you around $1.5 to $2 million, and that's crazy. Say if if the average house price is around $2 million, if you look at the average income in that area, it's just $75,000 a year. How, like you, so you have to work 30 years without any expanding to save for a house, for an apartment. That's ridiculous. So, I mean, so it depends on you. So if you want to, for me, let's say if I move to the West Coast, they have to pay me a lot to compensate for the environment, the bad environment in the West Coast.
Do you want to leave academia?
You mean terminate my job?
No, I mean, like, do you want to like go into the industry and just like stop being a professor or something? Like, would that be realistic?
That's one option, but I prefer to stay in academia. Over here, I got a lot of freedom. I can read papers and refresh my knowledge, and also like I don't have to. Let's say here, still I want to do research for now, but in the future, who knows? Who knows?
How many papers do you have to
if a tech giant job me an offer, let's say $2 million a year, I'm not going to refuse it.
They have to give you an offer you can't refuse, essentially.
Right.
How many papers do you have to publish per semester for your job?
Okay, so that's a very good question. In our department, there is no requirement. They don't set up a bars in that if you don't publish this, you are going to lose your job. But on average, it's like 2 to 3 papers a year. Okay? This is the average. Do you know how many do I got?
20, 15?
So I joined the department like 4 years ago. So I got, let me see how many. I'm just going to check it. Okay, I think I got something like I think I got 35 in 4 years, in the last 4 years since I joined. So
9 a year, essentially.
So I mean, yes, that's my life. So just keep working.
How's the work-life balance for a professor?
Okay, so let me introduce this for you. It's interesting. Okay, in the US, there is probably you hear something called tenure track. Have you heard about this before?
Yes.
Yep.
Yes.
So do you know what that tenure track means?
They can't release you from your job.
No.
After the tenure one.
When you become tenured, but you're on track to become tenured.
Once you become tenured, as long as you don't make a very big mistake, the department or the college cannot fire you. It's like a permanent job. So, but in order for you to, so currently I'm a tenure track professor. So usually they give you 5 years. So it's called pre-tenure. So they give you 5 years. So to let you work very hard and prove yourself, prove that you are valuable to the university, so that in the 6th year you're going to apply for tenure. If you are approved, then you are tenure. So then you become literally you become one of the owners of the university. Actually the president works for those tenured professors. So because the president is not a permanent job, but those tenured professors, they are just permanent. So they can stay as long as they want. So I mean, before you are tenured in academia, you don't have your life, to be honest. You have to work extremely hard. It's like you in 5 years you need to prove, you need to show the university that give me a permanent job. So you're going to cover the cost of the rest of my life, basically. So in those 5 years, you have to work extremely hard. I'm in my 5th year, so I'm going to apply for my tenure in this September, and hopefully I'll be able to get it. And after that, I'll be able to have my life.
I see. So you're working like 80 hours or something like that?
No. In the first 1 or 2 years, I worked long hours, like 70. And now I work like, say, because I'm pretty sure that I'll be tenured. So because with this publication, and also I got a grant, so I got some funding, so I'm safe. Now I just work like, say, 40 hours.
I
Wait,
see.
Spencer,
Okay, that's
I have a question.
Sure.
Who do you like while during your research, when you don't understand something, who do you go to? Like, what's your top resource?
What's the top resource? Paper. And so if you don't understand a theory, go to paper or book.
Mm-hmm.
Okay. If you don't understand a code, if in terms of coding, go to Stack Overflow. There was a website called Stack Overflow, and also I use Reddit. In Reddit, there is some thread for machine learning. And people just help each other in that community. I love it.
No, like, but while researching, so let's say you're researching some topic and there are some things you're not able to, get together. Then what do you
Paper
do?
and book.
Paper and book.
Yes.
Mm-hmm. Okay.
by paper. Do you mean like peer-reviewed articles?
Yes.
Okay.
Something like what I showed you just now. Something like this. This was published by OpenAI. So yes. And something like this. Okay. So any more question for me? I think I think one student was just talking, but he was muted. Aaron.
Professor, I have a question.
Sure.
What do you think about software design? Like designing
Software.
software?
You want to be a software designer?
Yeah.
So what do you mean by designer? So design the interface or design the architecture?
Yes, both. I'm not quite really sure. But like,
Okay, the interface part is not worth. Okay, so usually those students from the arts, they got those jobs. They're more related to arts. But so if you want to be an architecture, that's extremely cool. That's probably the best job in this category, in the software engineering category. But in order to be a architecture or software architecture, you have to work at least 80 years of working experience as a software engineer.
okay.
Okay, and also you need to work extremely long hours, but you will be paid a lot.
Okay.
So I have friends who have this job, but in China. So he spent most of his time in hotel. So basically the company, to save his traffic time, the company just rent a permanent room for him in a hotel which is like 2 blocks away from his company.
Isn't that expensive?
Yes, he spent most of his time over there, eating, like dining and sleeping. Okay. So
So you did say that if you want to make money and you didn't want to work that too long hours, that you'd go into machine learning or cybersecurity.
yes,
Out of like those two, what if you're like elite or very skilled in what you do, like a top 1% person, what would give you the highest return on investment? What would get you paid the most? Machine
learning.
Machine learning? Okay.
Yes. In cybersecurity, you get more safety in your job, meaning that so once you get a job, your payment is going to be fine, and most importantly, it's very easy for you to keep that job. Or if you work in this side as a machine learning, if you do so you'll be paid extremely well. But the thing is that if your model, the machine learning model that you built crashed, you will definitely lose your job. Okay, so yes, this is more risk, but more, I mean, potentially more money, higher risk.
Good to know.
Okay, so okay, so this is the. Any more questions?
I have a question. Are you hiring undergraduate research assistants?
Research assistant. Okay, so I think I will talk about that later in our later in the semester. Because currently, I just got a grant to pay a student like somewhere around 6,000 to 8,000 over the summer for 10 weeks. In the summer. So I'm going to talk about that later when I get the I'll collect more information about that.
Okay.
Okay.
All right.
So
Fair enough.
okay. Sure. So okay. So then let's talk about the last data structure that we're going to learn today, hash table. So actually in Java, Java already provides the implementation of it, but I'm just going to introduce it to you. So far in terms of search, we learned two data structures. The first one is binary search tree, and the second one is RB tree. So the binary search tree can give us OH search complexity, where in the best case H is log n, whereas in RB tree it's guaranteed that we got O log n search complexity. Correct?
Yes.
So the thing is that can we do better in terms of search? We want to do better in terms of search, and here is how we do better. There is another data structure named hash table. So hash table can give us O1 search complexity, meaning constant time. So no matter how many elements do you store, it's guaranteed that you will get O1 search complexity. Okay, so then let's say how do we do that with O1 search complexity? So before that, I just need to introduce one function named the hash function. The hash function is a magic that giving an input x. X can be anything. It can be anything. It can be a number. It can be a document, or a string, a very long string, or it can be say a character. No matter what it is, it can be anything. So if you pass x to the hash function, we call it hash function, it will output a value, a random value y. So this value y seems totally random for us. But the beauty of this is that no matter how long it is, the length of y is going to be fixed length. Okay, fixed length. So first we know that, okay, no matter how long is the input, our output is going to be fixed length. Okay, so usually it's like the length is like 122 bits or 225 bits, 256 bits or something like this. And so this is one thing. And then the other property, another property of hash function is that, okay, so giving, so it's extremely hard for you to find two different input, x1 and x2, such that the hash of them is similar. Okay, so if we got two different inputs with the same outputs, we see there is a collision. With the hash function, it's extremely hard for us to get a collision. Okay, and so this is also the basis of Bitcoin or blockchain. So okay, it's extremely hard for us to get a collision. And then the third property is that, so giving y, if you're giving y, if you're only giving y, you cannot get x. You don't know what is the, if you're giving the output of a hash, so it's going to be computationally infeasible for you to reverse this function and get the input for the corresponding output. Okay, so these two are going to be, we say them computationally infeasible. So this is very serious. Computationally infeasible meaning that even though you are giving the best computer in the world, it's going to take you at least 200 years to finish the computation. So by that time, all of us will disappear. So
yeah,
this is the theoretical foundation of. So this is a hash function. So here, what you can say is that fixed length random output. So the random output, by random output, I mean that given the same x, still you are going to give, you're going to receive y, but the output for you seems totally say random to you. You're like, what the hell is the output? It does not convey any meaning. Okay, so this is the hash function. Actually, hash function is widely used in cybersecurity, and I think one of the most famous application is in blockchain. So in blockchain there is one thing called proof of work, right? I'm not sure if you heard about this before.
Yeah, it authenticates, right? Is that
Yes.
what it does?
No.
Oh, yeah.
So basically, so proof of work is this. Okay, this is I'm just talking about proof of work in the world of Bitcoin. In Bitcoin, the word is that. So the word is the proof of work is that. So basically, giving it's going to give you a challenge and a nonce. So you are giving a challenge and a nonce, and then your task is to find x such that you need to find x such that the hash of x plus n equal to c. Okay, the hash of the you are going to find x such that the so the hash of x plus n equals to c. So where c and n are given to you, okay, are the give input to you. So remember, okay, if you connect these two, it means that, so now you're giving the output c, and it asks you to calculate the input of that. So this is computationally infeasible. So the proof of work is that, so the proof of work is that you find an x which solve this problem, which means that you pay a lot of efforts in computation. Okay, so So that's why a Bitcoin is worth now, let's say $30,000 or even $50,000. It's because even though you are really lucky, it will consume at least 10,000 of electricity. So if you run your program to find this X, it will consume at least 10,000 of power for you on average. That's why a single Bitcoin nor is worth 30K or 50K. I don't know exactly. You have to be really lucky to find it with 30 by paying 10,000 of electricity bill. Okay, got it?
Yeah, makes sense.
Yes.
Yeah.
Okay, so the beauty of hash table is this. Okay, we are using this. So suppose that we want to store some values. Let's say x1, x2, x3 in an array. Again, in an array. Let's say here we got three values, or let's say four values. And we want to store them. In an array. So and then we want to perform some search, right? So the thing is that at the time of search, let's say if now I ask you, okay, let's search for the value. Let's search for the value x. Let's give a random value. Let's say we want to search for k inside the array. So let's say we store these values x1, x2, x. Okay, we're giving a sequence of values, and we want to search if k is inside this area. Okay, is inside. We want to search for k inside this sequence. So first, what we do is that for each of these x, for each xi, we're going to get its index by using this. Okay, we're going to apply the hash function over xi, and so it will say here it will give us a random value, right? It will give us a random value, a fixed length random value. So this value can be as large as 2 to the power of 126 or 2 to the power of 256, 128 or 2 to the power of 256. No matter what it is, we take the hash result of it. Let's say we call it hi. Hi is the hash of a certain value, and then we take the residue of the we use this. We take this hash result and modulate over the length of the array, of the array, and we take this value as the index of it. Okay, we store xi maybe over here, and next x2 over here, x3 over here, and x4 over here. Okay, so we store them over here by using the index calculated in this way. So the next time, if you want to search for value k, so the thing is that we are going to use hash k and take the residue of length. We are going to be able to find the location of it. Okay, so with one calculation, we will be able to find the location of it, and then we would directly go to this location of the array. If we see that if this value exists in the sequence, it's going to reside in that location. Otherwise, when we go to that location, we find that that location is just empty with no value in it. So we say that we don't find it. So basically, with hash table is basically an array, but the index is calculated by using the hash function. With this property, we will giving any value to search. We can just calculate the index or the location of it with one calculation. We don't have to go through all the values in the array. Instead, we can just to find the index, the location of the target. Instead, we just calculate the location of the target with the hash function. So that's how we got the O1 search complexity, by using hash table. Got it?
Yeah, makes sense.
So I think this is somehow very theoretical, but the thing is that so in the future you are going to use, definitely if you become a software engineer in Java, you will definitely use the data structure named hash table very often. So just keep that in mind. If you don't understand the math behind it, the magic behind it, just keep in mind hash table gives O1 search complexity. Okay.
Wait, O-N or L?
O1.
O1,
Constant.
okay. Okay.
No matter how many elements do you store in the data structure, in order to search for a single element, the time performance is constant, and this is the best search complexity that we can hope for. Any question?
No, I think it makes sense. I get it now. Mhm.
So basically, you can take hash function as a magical way, as a magic to tell us the location of anything. So then we don't need to actually search. We just need to get the location and go to get the value. Okay, so this is what I want to teach you regarding hash table. And then, so that's pretty much everything that I want to introduce today. Any question for me?
Are we going over hash tables in more detail later on?
No, that's pretty much what I want to introduce about hash table.
Are we going to implement it in the homework?
No, you are not going to implement that. You are not going to implement that, because if you want to implement that, you will need to use hash. Okay, you need to use hash function, and if you want to use hash function, you need to use a library called. If you want, I'm not sure about the hash function in Java, but in C++, there is a library called lib what? SHA or lib something. So I don't remember. I don't remember the detail. Oh no, lib SSH. Yes, lib SSH. And this is really difficult for you to learn, and to use that library is really difficult. And this one is, but if you go for a master in cybersecurity, you will need to learn. You will only learn it if you do master in cybersecurity. So that's why I'm not going to ask you to implement hash table by yourself, because it's too advanced for you.
Wait, SSH, you mean the secure shell?
Yes, lib
Okay.
SSH or no, it's not lib SSH, lib SSL.
SSL?
Or SSL or SSH. I don't remember it exactly. I did this maybe 7 years ago. So I implemented it 7 years ago. So I don't remember. So it's either lib SSH or lib SSL. So they provide something called SHA, SIG, or SHASH. They have SHA-125, SHA-1. They have SHA-1, SHA-2. So these are just two different versions of hash functions provided by the library. You need to use one of them. That's too difficult for you. So in your homework 5, you're only going to implement the binary search tree.
So I don't know if this question is a little soon, but what do you recommend us to do to excel in the exam?
Just pay attention in the lecture, understand how does the pseudocode work.
I see. Thank you.
Okay, so the other thing that I want to briefly talk about is about the homework. So last Friday, I received an email from a student asking me what is the correct output of that homework. So I think a lot of you are wondering it. I want to know what is the correct output for each homework. After you spend let's say 5 hours, 4 hours on it, you definitely want to check if your implementation is correct or not. So the thing is that throughout my lecture, throughout my class, I am not going to let you know to tell you what is the correct output. If you understand my lecture, it's very easy for you to infer the correct output by yourself. Let's just take the last homework as an example. So let me present from my desktop. So can I say it?
Yeah, I can see it.
Okay. So here, okay. So this is the pseudocode that I provide you for stack, and let's just go to the main function. So in the main function, we first create a stack whose size is 10, which means that it can store at most 10 values. So for I starting from 0 until 4, we're going to push the I into the stack. So here, after we do the push, what are the elements in the stack? How does the stack look like? So how does the stack look like? It's going to be something like 0.
0, 1, 2, 3, 4.
Yes, 0, 1, 2, 3, and 4. Okay, and next, for integer from I to 0 and I is less than 2, and we pop something. So here, basically, we're going to pop twice, right? So the first time, when we pop it for the first time, which element goes out?
The 4.
The 4th, it pops the last element.
Yes. And then in the second pop, we remove 3. So after that, the stack is going to be something like this, right? And then if you look at the function that I defined for the toString function of the stack, basically it will print out all the values in the stack. So if you got the implementation correct, so you will see the output like this: one line over here and one line over here. So so that's why I said that I'm not going to tell you what is the correct output. So throughout my lecture, throughout the class, either you can find the correct output from the slides, or you can infer it by yourself very easily if you understand the lecture. Okay, so one question is, what does params do? So you mean this one, the string args?
No, the one on top of it.
Sorry?
The one on top of it, the one that says
note, the
param
note.
args.
Sorry,
The
I couldn't.
comment, I think he's talking about the comment.
Oh,
Yeah, the
here, the
comment.
comment. So this is just comment.
Yeah, the one, yeah, that one right there.
Yeah, this is just the comment. So the add param. So this means that it's an explanation of the parameter of this function. So the parameter of this function is args. So basically, people use this way: add param of some input variable value and type in something over here. Say explanation. It is something. So you are just leaving a note first off.
Okay, thank you.
No problem. And actually, this is used more widely in Python. Let me show you something that I wrote. So for this, do I have to know this one? So because it has too many parameters, maybe this one. No. This one. Forget about it. So I cannot find an example in Python either. So Python code that I wrote. But this one no, because it has two parameters. Standard parameters. This one. No. So basically, you can take it as a here. See, this function takes two input parameters, and in Python, the convention of the node is that so we got this param and the variable name, and you add a couple of sentences to explain what's that. Okay.
Okay,
So,
thank you.
No problem. So that's what I want to talk about for today. And any question for me before we end our lecture today? No? So then that's it, and have a good night.
Have a good night,
Have a
Professor.
good night, Professor. Great
Thanks,
lecture today.
Thank you.
Thank you. Bye-bye.
Thank you. Bye.